Alright, hello people of science. We've already talked about RNA and versus DNA. Now we're going to talk about how that RNA is made through the process of transcription. So this one is going to kind of start to answer where are we going with all this and what does transcription actually do. Those animations in there, you can feel free to look at that or we will come back to that. Alright, let's talk about the big picture. We've just been talking about DNA. In this case right here, I want to think of DNA as almost like a CAD, or that's computer-assisted design drawing, like a 3D drawing. Think of them the same way for right now. Both of them are information only. They are great for long-term storage of information, passing it on to others, and it's the master copy. Everything is built off of this design, DNA and this CAD drawing. However, let's be honest, it's useless on its own. You know, if you have a dog and it wants a doghouse and you tell that dog, hey look, I have this awesome drawing for you, that dog will, well, it'll be confused because it probably doesn't speak English, but if it did speak English, it would probably say, this is useless, I can't sleep in that. Why did you waste your time on that, stupid human? So with DNA or with this CAD drawing, you actually have to build something with it in order for it to be really functional. This is where RNA comes in. RNA is almost like blueprints, you know, something where you take that CAD drawing and you start actually pulling measurements off of that. Now, this is still information. I mean, you obviously can't live in it, but this is a lot more useful for actually building. I know what pieces I need to make. This will make actually assembling it and putting it together much easier. However, you don't want to do long-term storage. You don't want to have a whole bunch of blueprints laying around. It's a lot easier to have like something like a computer file right here. That'd be a lot easier for sharing and passing around rather than having to deal with a blueprint. RNA, or this blueprint, is a temporary disposable copy. I don't need it long term, but I definitely need it to build things. Well, let's talk about the final thing, the thing that we've been dancing around for a while, protein. Protein in this case here is the finished product. This is useful. It does something. This is what your dog could actually sleep in and wouldn't give you the stink eye for making a 3D drawing for. Your dog would be very happy with this. This is the point of it. However, you cannot make more dog houses or more protein without those instructions. So you can't just say, just, copy the dog house. Well, you have to go back to the DNA of the RNA before you can make more of this. So it's useful, but if you want to make more, you got to go and start at the beginning here. I want to emphasize this. This protein, this is the entire point of everything. This is why we have DNA. This is why we even have that RNA in the middle. The entire point of all this is to make that protein. What's the point of doing this CAD drawing here unless you're doing it for just the fun of it? The point of it is to make this finished product here, is to make the actual doghouse. Alright, I want to show you guys this animation here. I'm going to go into it one more time, but I think it's a lot easier to just shut up and let the animation speak for itself. No, your microphone hasn't cut out. I'm just quiet right now. Maybe I shouldn't talk at all. Still here. Still here. Okay, now what we have right here you should recognize as DNA. I've got the A's, T's, C's, and G's. It's double-stranded. You can't see the deoxyribose instead of the ribose, but it's there. Here I have a strand of RNA, which you should recognize because it's single-stranded and I have the U's in there. You'll notice that I have just taken this part right here, the G, T, C, A, C, T, 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 and I've made a copy of it. Of course, it's slightly different because I have the U instead of the T, but still, I have essentially a copy of this one side here. That's the entire point of transcription. I started with this, I end with just an RNA copy. Alright, let's talk about it. Transcription, as you saw, the DNA is temporarily unzipped. You know, imagine you've counted out like a zipper that's on a luggage and you got two zippers. If you moved them back and forth, it's meant temporarily unzip it. I haven't damaged it. I haven't done anything to the DNA. It's just opened it up just a little bit. And from there, you're going to make an RNA copy from that DNA template. The enzyme that actually does this is called RNA polymerase. Maybe you remember before DNA polymerase makes DNA, in this case, RNA polymerase makes RNA, in this case, messenger RNA. So that's one that actually comes along and adds the nucleotide. So that big green thing you see in the background, that is my RNA polymerase. Temporarily unzips the blue, the DNA, and it makes that RNA copy to go along with it. However, as you saw before, wherever you normally have had a T, now you're going to put in a U. So here's my DNA sequence, ATG, CGG, CGT, and ACA. You'll understand why I'm saying those in groups of 3 later. But if I'm going to make an RNA copy of this ATG, the RNA other half of it would be UAC. Because normally I would want to have a T here, but in RNA I would have a U. T still pairs with A, that hasn't changed. Remember, this side is all DNA, this side is RNA. CGG would pair up with GCC, they're still complementary. CGT, well, C should be opposite G, G should be opposite C, and T should be opposite A, and there it is. And ACA, remember, wherever you would normally have had a T, which would be right here, now instead I'm going to have a U. All right, so here's just kind of a bigger picture of it right there. You can see that double-stranded thing is the DNA. Here's the mRNA copy that's being made, and of course the enzyme that does that is RNA polymerase. And this whole little area here we call a transcription bubble, because it's just sort of temporarily sort of opening up, but then it closes back again. Remember on the mRNA right here, I got phosphate sugar, nothing new there, but in this case here I have U, where normally I would have had a T. Now, before it can actually leave the nucleus, that RNA copy, it needs to be trimmed or edited or kind of pruned down just a little bit. So right here I have the alphabet, and you will notice in here, right now it's the alphabet, so it doesn't really have information, but I've buried a word in here. And in order to get that word out, I actually need to remove things. So look for all the capital letters in there and look for the word that's in there. Well, if you took the time to actually do it, you'd notice that the capitalized letters spell out ghost. So there is information in there, but in order to get that, I kind of have to trim out some of this stuff in order for that message to appear. That's kind of what RNA editing is like. You got to trim out a little bit here. And I'm so sorry. I'm so very deeply sorry from the bottom of my science heart about this. But their naming convention is backwards. You'd think that the thing that you remove would not be the thing that has the word in it, but it is. Introns are removed. Think of it as like intruders. If you found an intruder in your house, you would probably want to remove them. The things that stay are called exons. Think of them as excellent. And again, I'm so sorry that it's backward. The in thing gets out and the X thing stays in, but go with my way of remembering it. Introns are like intruders. If you find an intruder in your house, after you probably do a lot of things to them, or like shoot or stab, well, don't do that, but just don't, whatever. You want them out. Introns are intruders, you want them out. Exons are excellent, you want them to stay. So if here I have a sequence of RNA, so this is just a big sequence of RNA right there going all the way across. This part here is an exon, I want that to stay because it's excellent. This part here is an intron, I want that gone, it's an intruder. And this exon here, I want that to stay, that is also excellent. So in the editing, the final draft will be nothing but exons. All the RNA will be nothing but exons when all is said and done. In RNA, you have 4 letters, A, U, C, and G. Think of it as like the English language, which is probably the only one I speak, kind of. There are 26 letters that we build all of these 600,000 words that are in the English language with. RNA has only 4 letters, A, U, C, and G. Now from this, you build words. Imagine if all of our words had to be a fixed length. In the case of RNA, all of those words have to be 3 letters long. So here I have GCA, that is a word of RNA, and it is called a codon. You need to know that term there. So here you can kind of see the RNA backbone, phosphate sugar, phosphate sugar, phosphate sugar, and then I have 3 bases on there, A, C, and G, and collectively you call those 3 letters a word of RNA called a codon. Alright, I want to go back to this animation just one more time since you should be somewhat familiar with it and just kind of show you piece by piece. Don't worry about the promoter right here, but here's my RNA polymerase. Remember, that's the part that comes in, it finds a special region, and it starts making that RNA copy. Wherever you would have normally had a T, that gets replaced with a U. Comes to the end of it, pops it off, and this red part right here is my mRNA. That was the entire point. Take this DNA, make a single-stranded temporary copy of it that will be used for building later. All right, that's it.